So in this session, we learn about few of the basic antenna parameters. And among that, let us start with the first one, that is radiation pattern. By the name itself, it is defining what it is. So it is a pattern, means it is a diagrammatic representation and of what? The diagram representation of the radiation of an antenna. As we are discussing this term in relevance to antenna, the radiation pattern of an antenna is a pattern which is obtained by means of the radiation characteristics of an antenna. That is what we can define in a simple way. But in particular and technically, we can define a radiation pattern of antenna as a mathematical function or a graphical representation of the radiation properties of an antenna as a function of space coordinates. And always the radiation pattern is determined in the far field region of an antenna, and it is represented as a function of directional coordinate because the radiation pattern can be obtained in three coordinate system and it can be obtained in different parameters. That's why we understand that the function of the radiation pattern can be expressed as a function of directional coordinates. And the radiation properties of the antenna includes the power flow density of the antenna, radiation intensity, field strength, directivity, phase, and polarization of the signal. So, a radiation pattern of an antenna is the graphical representation of the radiation properties of the antenna as a function of space coordinates. This is the definition of radiation pattern. It is a graphical representation of the radiation properties of an antenna as a function of space coordinates. And when we are representing the radiation pattern in mathematical equations or as in on a graph, then the three important parameters which we keep in mind are the amplitude of the signal, the phase of the signal, and polarization of the signal. And that's the reason why when we are defining the radiation pattern, we consider the functions of angular space coordinates, that is theta and phi. So we can represent the radiation pattern in terms of amplitude, in terms of phase, and in terms of polarization. There are three different forms of radiation patterns or as the types of radiation pattern for an antenna. They are field pattern, power pattern, power pattern in linear scale, and power pattern in dB scale. So, what is field pattern of an antenna? Means, when we obtain the radiation pattern of an antenna, keeping the antenna in either H field or else in E field, then we call that radiation pattern as field pattern. That is, a field pattern of an antenna is a representation of the plot of magnitude of the electric or the magnetic field as a function of angular space. So when it is field pattern, it is either we can obtain the radiation pattern in H field or in E field. So coming to that, let me take an example of a on type of antenna. A on type of antenna, or else I can take the example of a short dipole antenna. So if this is the representation of a short dipole antenna, which has pole 1 and pole 2, as it has two poles, we call this as dipole antenna. And whenever this dipole antenna is placed parallel to the axis, parallel to the x-axis, then we call that the or the antenna is operating in H field. Suppose if I place this antenna in vertical direction, that is like this, and whenever the waves of propagation is parallel to the electrical lines of force, then the radiation pattern which I obtain is called as E field radiation pattern. So the radiation pattern means that whenever the antenna is placed in this direction, the radiation of the signal will be emitting like this, and when the rays are emitted, there is a beam formed in this x-axis, in accordance to the x-axis. This is what we call it as radiation. The blue color line which has been explained, this blue color line is what we call it as radiation pattern of an antenna in H plane. And this is what we call it as field pattern, because the antenna is placed in parallel to the H field. Yes, coming to the second case, that is when the antenna is placed vertical, or as when the antenna is placed in parallel to the electrical lines of force, then the signals will emit in perpendicular fashion. So, as this is the outer surface of the dipole antenna, and this is the input signal what we are giving, the signals emits in this direction because this is the opening of the mouth, and there is a radiation pattern which is obtained in the E plane. So, this is what we call it as E pattern. So, the field pattern of an antenna can be represented as a plot of its magnitude of the electric or magnetic field as a function of angular space. The second type of radiation pattern is power pattern. So when we are talking about power pattern, then it is a plot of square of the magnitude of the electric or magnetic field as a function of angular space. It is the square which we need to consider. So when you are representing in terms of power pattern, so when we are representing in terms of power pattern, if this is a short dipole, this is the input microwave power supply, what we are giving as input for the antenna, and this is a short dipole. Here, whenever it is placed in the magnetic lines of force, then this is the radiation pattern what is obtained. But when the radiation pattern is obtained, there are three lobes which is obtained. That is, this is what we call it as major lobe, where the output power is maximum. This is called as major lobe, or as this is called as main lobe in an antenna. And these lobes are called as side lobes. This is called as side lobe, and this is called as back lobe, or it is also called as minor lobe. So, when we have the radiation pattern in forward direction like this area which is shaded by red, this is the area where we have the radiation pattern. And from this radiation pattern, we can express this in terms of power beam width. We can represent this in terms of beam width. Means depending upon the width of this beam, that is this radiation pattern, water is there, we will calculate what is the beam width of the signal. Beam width, it is not bandwidth, it is beam width of the beam. And whenever we square this value, then we get the complete full first null beam width. So this is what we call it as power pattern. And that's why power pattern, we define that the power pattern represents the plot of square of the magnitude of electric and magnetic field as a function of angular space. So this is power pattern in linear scale. And the power pattern can also be expressed in decibel scale, that is dB scale. So when I convert this value of power pattern into dB, then I call that the power pattern is represented in dB scale. In the lab, when we are performing the experiments in relevant to short dipole antenna and the Aguda antenna, normally we place the dipole antenna in either E field or in H field. We obtain the output power pattern in dB, because in our lab, we have the power meter which can display the power in dB. So the radiation pattern what we obtain in the lab is a power pattern which is represented in terms of dB and which reflects the off power beam width. The beam width is represented, and by the value of beam width we calculate what is the gain and directivity of the antenna. So this is what we call it as a radiation pattern. A radiation pattern is the graphical representation of the radiation values that has been given by an antenna. Always a radiation pattern consists of three lobes. That is, this is the main lobe, this is main lobe, and the lobes which are smaller in dimension are side to the main lobe. These are called as side lobes, side lobe, and the antenna also radiates in the backward direction where the nominal power gets dissipated, and this we call it as minor lobe, or I can also call this as major lobe. Major, minor, and side. Major lobe, minor lobe, and side lobe. So a radiation pattern consists of three lobes, that is the major lobe, minor lobe, and the side lobe. Or I can also call the major lobe as minor lobe and the my major lobe as main lobe, or I can also call it as minor lobe as back lobe. So these are the three lobes which is present in the radiation pattern of an antenna. And the radiation pattern can be explained arrived in field pattern, power pattern in linear scale, or power pattern in dB. So when we plot the radiation pattern in terms of amplitude, we have the field pattern, that is a plot of the field in electric field or either in magnetic field on a linear scale. And power pattern means it can be expressed in terms of linear scale or dB, that is E square or H square. So this is the diagram of the radiation pattern in three-dimensional and two-dimensional view. So this is a two-dimensional view which we plot in our lab also. When you conduct the experiment in relevance to antenna, you will be plotting this radiation pattern. After obtaining the values by conduction, you will plot this radiation pattern. So this is what the two-dimensional view. This is called as major lobe, or I can also call it as main lobe. And this is what we call it as off-power beam width, and this first null beam width. The beam width between the first nulls are called as first null beam width. Fn stands for first null beam width and HPBW stands for off power beam width. That is the major lobe, and this lobe is what we call it as side lobe, and there will be one more lobe which is called as back lobe, LOB, lobe. So here we can see at different angles we have got the radiation pattern, and here this is what we call it as a major lobe. So this is in two-dimensional view. But in when we are taking in representing in Cartesian coordinate system, that is in three-dimensional coordinate system, it is x, y, and z coordinate system. But when we perform experiment in the lab, we just write the values in two-dimensional. So what does this plus and minus on the lobes indicate? That is the plus and the minus values on the lobe indicates the relative polarization of the amplitude between the various lobes, which changes as nulls. And whenever the pattern achieves its upper beamwidth, that is minus 3 dB points, then the field pattern at minus 3 dB will be maximum, and the power pattern at its 0.5 value will be maximum. But whereas power pattern, when we are representing in terms of dB, at minus 3 dB, the value will be maximum. So field pattern at 0.707 value will be maximum. This one you need to keep in mind because it can be asked as an MCQ for your lab or for the exam. So field pattern value is 0.707 and power pattern value in linear scale is 0.5 and power pattern value in dB is minus 3 dB. So this is a polar pattern, which the radiation pattern is obtained expressed in x, y, and z coordinate system. Here we can see this is the major lobe, which is represented in diagram, and the smaller one, a tail like of thing. This is the back lobe, and there are three side lobes. And this point represents the first null beam width, and the second layer represents the off power beam width. So this is representation of radiation pattern in polar pattern. And we can also represent in linear pattern, means on a linear scale, that is in x and y axis also we can represent. So here we can see this is the major lobe where the radiation intensity is maximum, and the side lobes are represented beside this. These are the side lobes or the major lobes, and these are the back lobes. So this is how we can express the radiation pattern in linear scale or linear pattern. And this is what we call it as normalized field pattern. Normalized field pattern means say that we will be representing in terms of modulus. So in linear scale, suppose if I take an example where there are 10 number of antennas which is placed at a distance of lambda by 4 each, then the upper beam width would be 38.64 degrees. In same way, if I want to obtain in linear scale also, then the final value will be 38.64 degrees only. Suppose if you are representing in terms of power pattern, then also it is 38.64. So you just please, the notice can, the difference can be understood. In 2D normalized field representation, this is the 2D normalized field pattern representation, and this is power pattern representation. This is normalized power E square pattern of linear array, and the power can be expressed in terms of radius. So this is in terms of the angles, power representation. So in this session, you have learned about the radiation pattern of an antenna. So the radiation pattern of an antenna is the graphical representation of the radiation properties of an antenna in space coordinates, in different space coordinates. The radiation pattern can be of three types. One is field pattern, power pattern in linear scale, and power pattern in dB. And always a radiation pattern of the antenna will have three lobes: the major lobe, the minor lobe, and the side lobes. Or they can also be called as main lobe, back lobe, and the null lobes or as null points. The radiation pattern can be obtained in two-dimensional or three-dimensional view. And we can also obtain the radiation pattern as field pattern or power pattern. And whenever the radiation parameters is expressed in terms of field pattern, its maximum value is 0.707. When the radiation pattern is expressed in power pattern, its value is 0.5, which is maximum. And when you represent in power pattern, it is minus 3 dB. At minus 3 dB, the value of maximum power is at minus 3 dB point. This is representation of the radiation pattern in polar pattern. This is the linear pattern. And this is the normalized field pattern. In normalized field pattern, whenever there are more number of elements in the field, then normally it is considered as an array. And then we finally average the off power beamwidth value for all the antennas, which will be the final summation. So this is a 2D normalized field pattern, and this is the 2D normalized power pattern of a linear array. So like this, we can obtain the power pattern and field pattern on different scales. That is, the one is the linear scale, and the dB scale for an antenna. So this is what we call as a pattern lobe. The pattern lobe is a portion of the radiation pattern with a local maximum. And as it was explained earlier, there are three lobes. One is major lobe, minor lobe, and side lobes and back lobes. So these are the minor lobes and back lobe, which is named either way. This is major lobe and the side lobes. So pattern lobes and beam width, where off power beam width and personal beam width can be calculated by the use of radiation pattern. So this is all about the concept of radiation pattern in relevance to antenna. The radiation pattern is a very important parameter for an antenna, because whenever an antenna radiates, the radiation pattern analysis can be done, which leads to the calculation of the off power beam width. And by knowing the value of off power beam width, we can calculate the directivity and gain of an antenna. That's why the radiation pattern of an antenna is a very important basic parameter. So always by calculation of by obtaining radiation pattern of antenna, we will be able to derive, or else we'll be able to know what is off power beam width, what is Fresnel beam width, and also what is directivity and gain of that particular type of antenna. So radiation pattern is one of the very important feature, or is very important parameter of an antenna.